fundamentals here. Today, talking about basic purpose, or review basic statistical terms. And again, we'll move through this pretty quickly. A lot of this is going to be basic review for people. So, statistical procedures, why do we need to have these statistics? Why do we sort of drag you all kicking and screaming through these types of classes? Major situation, or sort of one of the things we do at a very basic level, is we can use some of these statistics, these procedures, to go through and take large amounts of data and start to organize it in ways that start to make some sense, start to give us a general sense of trends within data. So here we have a small array of data, number of drinks per month, where we've got a group of students. How many we have? 11, 66. I don't know, that's a weird sample size, but we get weird sample sizes sometimes. 66 people asking students how much they drink per month, okay? Who are my alcohol researchers in here? Okay, is this a lot for students to be drinking?
Looks like it.
It looks like it, right? But it's hard to get a general sense for sort of what this looks like, right? And so what we can do is, if I say on average this sample is drinking about 15.5 drinks a month, is that a lot or a little for college students?
A month?
Yeah.
I would say it's not that much.
Not that much. Okay, so maybe this is just a general, not an at-risk, average student sample, right? But if we look at standard deviation, is 12.4. What does that tell us? Let me know.
That it's that on average they drink anywhere from 3 to quite a bit, so 37, 38.
Right, so we've got some variability in this set, right? So we've got a point estimate for, on average, what people are drinking, but this would suggest that we have quite a range of drinking behavior, at least as reported in this sample. Our range estimate, 45, we've got everywhere from 0 to 45 drinks a month. So we've got a wide range of drinking behavior within this sample, right? This three very easy to calculate statistics give us a much better sense for what's going on in terms of our behavior here than just kind of trying to eyeball some of this, right? We can also go through and plot this out graphically. We're going to work a lot with visual representations of data. This is just a tremendous way to represent things. We don't do a good enough job in our applied research of graphing things out. Like, this is a very nice way to go through and show trends in terms of what's going on, right? Here, even outside of mean, standard deviation, and range, this gives me an even better sense of what's going on, right? I can say, well, looks like modal people aren't actually drinking a whole lot. So I've got a lot of people who are drinking very little, some who are doing a little bit average, then we got a group that a bimodal thing is, see, these are people who drink very little and people who drink a fair amount, and then we've got some people who are kind of outliers dragging that out there, right? And so this histogram gives us a very nice picture of what's going on. Again, thinking about not just using statistical or point estimates of different figures, thinking about how we can represent data graphically to go through and provide a good sense of what's going on in our data, okay? So we can go through organized sets, get an idea of general trends. Also gives us, provides us with tools for developing an objective assessment of relations between different types of variables, right? This gets us out of the realm of opinion. Well, I think that this is a related thing, or I think these two things go together, where we can actually start to test specifically the strength of relations between different variables, okay? So my research is in trauma, post-traumatic stress disorder, anxiety types of stuff. You all will become experts by association, because I need to give you data sets, and these are a lot of the data sets that I have. So, but early in my graduate career in Buffalo, I was at UB, lab that we had worked with survivors of motor vehicle accidents, right? And so we say in a sample of 334 individuals exposed to traumatic injury, 248 reported chronic pain after the accident. What we're interested in is the degree which pain status, yes or no, is associated with trait level anxiety, okay? If I wanted to test this, what are some of my options? What could I do if I wanted to test whether or not there is a relation between trait level anxiety and chronic pain status. Amanda?
I put histogram for a lot of things on the
Okay.
test because that's the word what kept coming to mind. But
So we could do
kind
that.
of a best fit, you know, like a correlation between the two is what I'm
Okay, yeah.
thinking, and pull in a best fit line.
We could look at a correlation, absolutely. What else could we do? So we've got two groups, yeah.
Could you do a t-test?
A t-test, right, would also work. And actually, your t-test and your correlation are functionally, they're identical tests, they're equivalent, right? But we could look at this a lot of different ways, and we have different options. And the option that we use is going to depend on what we think makes the most sense. How is this going to most effectively communicate the relationship of these data to someone? Here, we could use a t-test, right? So we could look at average levels of trait level anxiety among people who don't have chronic pain and those who do. And if we run that statistic, we get a test statistic of 3.46, p-value less than p equals 0.001. So we would call that a statistically significant effect, right? We would say that there's a reliable difference in chronic pain between people with and without, or excuse me, trait anxiety with and without chronic pain. But I don't know. I got a big sample. That might be a big difference. It might be a little difference. I don't know. So I can calculate an effect size, right? Here's an effect size. It says I've got an effect of 0.44. That's almost a medium effect, right? That's saying that the average difference in trait level anxiety for someone with chronic pain without, I've got about a half a standard deviation difference right there, right? That might not mean a lot to you right now, but as we go through, by the end of the semester, it will, right? We could also just look at the average difference, right, and then calculate a confidence interval around that, right? So this isn't all the people in the universe who have chronic pain. This is just a subsample of accident survivors who have chronic pain. This is just a point estimate that we're hoping reflects a larger relation between these two variables, right? And so we could say, well, in our sample, we see an average difference of about 5.7 points on our trait anxiety scale. But given what we know about error in our data and things like that, the actual population difference, reasonable estimates of the population difference, anywhere from about 2.5 to 9 points, right? So it gives us a sense for how accurate our data may be. So this is what we're guessing. This is our best guess, but reasonable estimates could vary quite a bit with this, right? So these are all different ways to go through and do this. We could throw up a bar graph, right, and have confidence intervals here, and sort of go through and plot this out and see what their difference is, right? We could also run a correlation, right? Now here, we could say run a correlation between these. Get a correlation of 0.4. This gives us an indicator of the strength of the relationship. We can calculate, again, a confidence interval around that correlation. We say that correlation, our best guess is 0.4, which again is going to be just right under a medium effect, but it could range anywhere from 0.3 to 0.48, right? So we've got some variability there. P-value is the exact same because these are equivalent tests, right? You could do any of these. All of these are reasonable ways to represent this question. It just depends on who's your audience, what am I trying to say, what's most important, right? With these data, I'd probably go with some mean difference, right? Because I've got two groups. Mean difference kind of makes, I can see that in my head. This is also a fair representation, but a little bit more difficult. But there may be times when this, for my purposes, is a more efficient way to communicate information, right? So wanting to know what are my options, what's the best way to go through and do this, and then understanding the strengths and limitations of different approaches. Our statistics also give us a language for professional communication. We're going to talk a lot about the limitations of our whole inferential statistics procedure, and there are many that we've talked about for a long time. Unfortunately, that's kind of the best option that we have, but what we can do is if we're all talking the same language, we can at least all agree, well, we at least are provided with the same information so that we can go through and pull things apart, right? My t-test is not any different than Layla's t-test, right? It's not different than Laura's t-test and our names, so we'll do that. But if I say this is the difference that I found and these are the methods I used, I know exactly what's going on, okay? Anybody have a chance to start reading through papers yet? Anybody get a handle on the Wilkinson paper? This is a phenomenal paper. This is an excellent, like you should, if you've got space on your body, you could tattoo it on there somewhere. That would be cool. It wouldn't be weird. I mean, this is from '99, right? You might as well have written this yesterday because all of it stands true, right? Some of the things I think that are important to highlight within this paper, it talks about more important than choosing a statistical package is verifying results, understanding what they mean, and knowing how they're computed, right? I'm not going to get into this right now, but as our computing power increases, there are certain types of analyses that become open and available to people, which is a very good thing. But it's not a very good thing if people don't understand what's going on, right? You don't want your surgeon to have a scalpel and a buzzsaw and be like, oh, well, I read some stuff, and if I cut right here and poke this exactly the right way, you should be good to go, right? You want that person to know what they're doing, why they're doing things along those lines. Statistics are no different. Maybe not a life or death situation, but it's the same type of principle, right? So not just plugging things in and hoping for the best. You don't want to report things without understanding how to statistical computer what they mean, right? Just because you plugged something into a program and it gave you an answer doesn't mean that it's right, it's correct, even if it's what I told you to do, right? There's several different things that can go wrong in this. You need to be able to go through and take efforts to assure that what you're getting are reasonable given the data, right? This is a big thing. Anybody do like psychophys research? No? A little bit?
We did a little bit with heart rate variability.
Okay, heart rate variability, right? So I'm going through and I punched some stuff into my computer and I got heart rate variability on average is 147. It's probably not that's probably not a reasonable value, right? But if I don't know up from down, I'm just going to report that because I don't know any better. If I understand what I'm doing, you should be able to identify that this is not a reasonable answer. This starts to become important as you're going through your data sets, right? If you get an effect size, anybody who's familiar with effect sizes, just Cohen's D in general, right? So I go through and I run my data and I find I got an effect size of 15. Is that reasonable? Probably not. That seems high, right? What I probably need to do is go back through and figure out where I made a mistake in my calculations because I've identified that this is not reasonable given the data, right? If I find that age is negatively correlated with income, I've probably got something going on backwards, right? And so this is where it starts to become important and looking at your data and saying, literally, what is this saying? Well, it's saying as people get older, their income drops. And so we're saying that on average, if I'm looking at income, I should be 15 and not 54. That doesn't make any sense, right? So we need to go through, recognize this, and making sure that the things that we're reporting is reasonable. Also wanting to check underlying assumptions required for analyses are reasonable, right? I'm going to say, oh, I'm going to run this analysis because I can, and if I stick it in SPSS, it's going to give me an answer. But if I violated all the underlying assumptions of the test, I have no confidence that these results are valid, right? Basically, we're saying, all right, under these conditions, right? These are what statistical assumptions are. It says under these conditions, if you run this test, you'll get something that should be relatively valid, right? But I go through and I run that test under none of those conditions, and then I want to have, say, oh, this is different than that. You can't do that, right? You violated all the basic assumptions of your test, and I don't know what we've got going on, right? So this is where we have to go through, and it's our duty as applied researchers to make sure that we know what we're putting into that black box, right? And then finally, when we're interpreting effects, think about credibility, generalizability, and robustness. Are these effects credible given results of previous studies, right? If I'm a trauma researcher and I find that rates of people with PTSD are operating interpersonally at a much higher level of functioning than people who don't have PTSD, that's a weird thing, right? That doesn't seem reasonable based on what we know about levels of psychopathology. And so what I need to do is either I got something weird going in my data, I've calculated something wrong, something's going on, right? I don't just report that and say, well, I guess that's the data, right? We need to go through, take a check. No substitution for common sense. Think about what we're doing. Again, we're not just running numbers to run numbers. As psychologists, we're trying to make some inference about human behavior, right? And if it doesn't make sense, that should be a red flag to go back through, double, triple check what we've got going on to see what's going on with things, okay? So again, this is a fantastic paper. Make sure you go through and read it. Gives a nice overview of kind of a manifesto for what we're trying to do with our analyses. Questions on any of this? All right. Basic terms and concepts. Population. If we're talking about a population, this is all the individuals of interest. Okay. Populations specific to a study vary widely in size. Someone give me an example of a population. Yeah.
College students.
College students. What college students? All college students?
Yes.
Okay. Is that university students or people in community colleges?
Universities.
Just university students. What about online students?
Just the ones that go to.
Just on campus students, right? So in America or in other countries?
In America.
Okay. So we start to get what our population is. It starts to become very, very complicated, right? Unless we want to say our population is all humans on the planet, it starts to get very specific, right? My population might be very, very small, right? But as we're going through and running our statistics, this is an important concept to think about. Who am I trying to generalize to? What's the population I'm pulling my sample from? And having a good sense for who that, we don't do this enough. We just say, oh, population is humans, and so all over the globe, and I'm going to pull freshmen from intro psych classes, right? Sometimes that's going to make a difference, sometimes it might not, right? But one to think about this is we can also get kind of abstract in terms of our populations, right? Let's say you have in your experimental study some sort of experimental manipulation, right? Who's your population? Well, it's a hypothetical population of all people who would potentially be subjected to this experimental paradigm, right? So if my population, if my manipulation is showing someone some film clip of something, right? Then my hypothetical population is all people who would watch this thing, right? Now I've got 20 people who watched this thing, but in theory, I'm assuming that the data that I'm getting from these people who are in my study is going to generalize to all people who would hypothetically watch this, right? And so same thing with treatment studies, right? I've got a new treatment for depression, and what I've done is I've got 10 people in there. Well, my actual population are all possible people who would be subjected to this treatment, right? Which starts to get a little bit more abstract, right? As opposed to all college students on camp, or all on-campus university students in the United States, right? That's an existing population. A lot of times when we're working with our experimental studies, we're talking about populations that don't actually exist, right? They're hypothetical populations. But this is an important and tricky concept to think about, okay? APA task force, so the interpretation of results of any study depends on the characteristics of population intended for analyses, recommending to define the population, petitions, stimuli, studies very clearly. Again, this is something we don't think enough about in our studies. Who do we expect this to generalize to, and did we actually pull from that population? The answer is almost always no with this. It's something to keep in mind. Okay. Sample, on the other hand, these are people we've selected to represent the population. Random sample serves as our gold standard. Do we ever have random samples of a population? Never. Never, never, never. This is our gold standard, and from a statistical series standpoint, things start to break down when we don't have random samples, right? Now, if the option is collect non-random samples or don't do research, we'll collect non-random samples, but we always need to be thinking about the implications for that. Generally, a bigger sample is a better sample. Why is this? Who have I not picked on?
Haley.
Haley, yes.
Typically more accurate when you have more data.
Yeah, why is it more accurate?
Because you can look into red outliers or usually abnormal.
Okay, cool. Generally, if I've got, if I want to look at income of college students, and I collect 2 people, just walking through Prexis, better than nothing, right? But probably better if I get 100 people, right? Because maybe I get a trust fund kid coming through. He's got massive, not that trust funds are bad, but this kid just comes from a lot of money, right? And now my thing's way off base, right? Or maybe I grab someone who happens to be sort of come from a family with not a lot of means, right? And they sort of his income is negative, right? As we start to get more and more people, we start to be better at over the place. As we get larger samples, we get more stable statistics. We get more representative estimates of our intended population. And in terms of thinking about our statistical assumptions of different tests, we can tolerate a lot of nonsense in a larger sample. As our samples get increasingly smaller, it gets more difficult. So we're thinking about statistical inference, okay? This is our population. This is everybody we're interested in, okay? This is, if I want to know what the relationship between state anxiety and chronic pain is, this would be all people who have ever been in a traumatic accident, okay? All right? And so if this is my population, if this is what I'm interested in, why don't I just study the population? What do you think, Nick?
It's impossible to study the whole
It's
population.
impossible. Well, often,
For the
most
most
often, right? Unless my population is like 5 genetically modified rats that are the only ones in existence, studying the population is probably not a feasible situation, right? So what I do is I collect a sample. These are the people who we can test. These are the people who we do have access to, okay? And then what we do is we get data from the sample of the people that we do have access to. We run some statistics, and then we make some inferences based on those statistics about the population here, okay? This is a simple diagram, but fundamental to everything that we do with inferential statistics. This is who we're interested in. This is who we're trying to make assessments about, okay? Our statistical procedures used to make inferences about a population based on data we collect from a sample of individuals who we hope are representative of this larger population, okay? We never care about the sample. We're using the sample. Sample is just a means to an end. I don't care about my sample. I'm using you to make inferences about this larger population. You're only useful to me insofar as you're representative of the population, right? Do I need to use statistics to tell me whether or not trait anxiety is different with people with and without chronic pain in my sample? Why not? I can just look, right? I mean, average score for my people without chronic pain is 40. Average score for my people with chronic pain is 50. Are those two numbers the same? No, they're different, right? I don't need statistics to tell me whether or not, I don't need a significant value or p-value to tell me whether or not the values in my sample are different. What I want to do is I want to make an inference to say, given the differences that I'm seeing in this sample, do I have enough evidence to say that, yeah, in the larger population, there's probably a difference between people with and without chronic pain in terms of trait anxiety, right? And so people say, well, there's a significant difference in the sample, there's a non-significant difference in the sample. I don't care about the sample, right? There's the difference in the sample, and the sample's always going to be different, right? At least to some decimal. Like, the values aren't ever going to be exactly the same, right? If I just want to say, is this number different than that number, I don't need statistics to do that. I can just look at it and say, yep, they're different numbers, right? But what we're trying to do is say, do we see a difference that's great enough for me to claim that in the larger population, we've probably got something going on, okay? So this is going to be really important. We're going to start, when we get into hypothesis testing, I'm going to ask you guys to start writing out your hypotheses. Remember that our hypotheses are always about a population. We're never trying to make inferences about a sample, because we don't need to, because I can just look at it and tell you what those are. We're always trying to, our population is always what we're interested in here. Okay. Questions on this? Yes.
I know that in psychological research in particular, our samples can be, or even our population can be very, very specific.
Mhm.
For example, there aren't a lot of people with schizophrenia to begin with, but
Mhm.
if you want to look at schizophrenics in the LGBT community, for example, how would you go about doing that if your sample is really small?
Well, it sort of depends, right? And this is the limitation in terms of time and resources and stuff. This is something that will come up in your comps, right? Sometimes our comps questions are too narrow, and there's no actual studies on what outcomes in schizophrenia in the LGBTQ community are, right? And so then we're like, oh boy, I don't know, right? And so we start to get into specialized types of research, but there are people who have developed programs that have access to certain communities and things along those lines, right? Now, if I'm looking at ventricle size, and if you're not familiar, so diagnosis of schizophrenia has been associated with size of ventricles in the brain, right? If you're looking at that, something like that, I wouldn't expect that to, on a basic physiological level, that to be a different situation in members of the LGBTQ community versus not, right? So that, I'm fine to just look at people with schizophrenia in general, right? But if I'm looking at
Pro-social relations.
pro-social, interpersonal outcomes, sort of access to employment assistance, things along those lines, that's a very different thing, right? And so these are the types of things we need to be thinking about when we're developing our research. What is my question? Who do I have access to? Can I answer that question with people I have access to? And then taking a fair assessment on that before we drop in a bunch of time, effort, and resources into a giant project that we can't publish because your reviewers say, well, it's not actually who you're looking at or trying to make inferences to. So this is where your statistical methods and your research and your design stuff start to interact. Other questions about this stuff? All right, cool. Again, just review on terminology: variable, some characteristic condition, changes or have different values. If we've got something that doesn't change, that's a constant. Okay. Someone give me examples of variables. What's a variable?
Height.
Height is a variable. Yes, I am taller than Angeline. Angeline weighs a lot less than me, right? These are all variables. Height, weight are variables. What else are variables?
Sex.
Gender, sex, right? Gender identification, right? Certainly. What else? Yeah.
Things like depression or emotions.
Depression, emotions, right? All of these things, these are things that change across people, right? These are things that if I bring people in, different people have different scores. This is a variable. This is something that we can go through and study, okay? Excellent. If we're talking about a parameter, this is going to be something that a characteristic that describes a population, indicated by our Greek symbol here. What's the hypothetical average score for the population of humans in terms of intelligence as assessed with standardized tests?
Is it 100?
100. Average IQ score is 100, right? It's kind of an artificial number, but the idea that in general, right? So if I look at the average score on an IQ test, that's a population measure in theory, okay? Statistic, this is a characteristic that describes a sample, right? I go through and I run IQ tests on all new doctoral students into psychology programs. What's my sample score likely to be? Above or below 100? Above 100. It's okay, you guys can say that. Statistically, you're smarter than the average person by sort of being and making it this far through your education, right? But this is going to be a sample, okay? But if I were to go through and take a IQ test of everybody here, right? That would be a sample of, presumably the population we're drawing from is going to be all graduate students in doctoral programs, I guess, ish, right? Want to think about who's the population we can start to apply these statistics to, okay? And again, we don't know this, right? I mean, so some of the first inferential tests we'll talk about are one sample t-tests, right? One sample t-test, we're comparing our sample value to some known population and standard deviation score, but we don't use these a whole lot because it's rare that we have values for a population, right? What we're generally doing is we're working with statistics from say an experimental sample and a control sample, and we're working on analyses with that to try and make some inference about, would we expect a true difference or a reliable difference between this population and that population based on the statistics that we've gathered? All right. Questions on variables, parameters, statistics, things like that? Okay. Descriptive versus inferential statistics. Our descriptive statistics, these are summarizing, organizing data. We're looking at averages, tables, graphs. We've got a box and whisker plot here, underused in psychological research. You'll argue overused in this class, but wanting you to go through and think about graphically how do we go through describe data in ways that make sense and are helpful. Our inferential statistics, these are our statistical tests, right? This kind of gives us a picture of what's going on. Our inferential statistics, these are the tests that we're running on samples to try and make generalizations to populations, right? So these are correlations, t-tests, ANOVAs. These are things that have p-values associated with them, okay? We'll get into the nuts and bolts of inferential testing. These are almost always based on some known or hypothetical, under some certain mathematical standards, known characteristics, right? And based on what we would expect, assuming no difference, would these, the data that we've, how likely is it that we would obtain the data that we've found, assuming what we would expect given no difference in these populations, right? And you'll read a lot of articles about this. We'll get in the nuts and bolts of this. This is all starts to become important because it helps us provide reasonable interpretations of data that's out there, right? People say, well, my sample of 15 and my sample of 10, I didn't get a significant difference on some outcome across these two, so there's no difference between these groups. Well, that's wrong, because there is a difference between those groups because the scores aren't the same. By definition, these two groups are different. Now, we may not have enough evidence to reject the null hypotheses that there is no difference, but we're just kind of in a I don't know situation here, right? And so making sure that people are making reasonable interpretations based on the data that they've obtained. All right, questions about descriptive inferential stuff? All right, sampling error. All right, sampling error. This is the error or discrepancy between a sample statistic and a population parameter, okay? This is all sampling error is, right? So, we design our sample to be representative of the population, right? If we're doing our very best work, let's say that I have, by some magical process, access to all on-campus university students in the United States, right? And I say, I'm gonna go through and randomly select, I don't know how this works out, but it's a hypothetical, so let's say it does, right? And I can go through and I can say, I'm gonna sample 100 people, 100 students, on-campus students from all universities, because I wanna know starting GPA or high school GPA of college freshmen of all on-campus students from all universities in the US, okay? And so I've done the very best, gold standard approach to doing this. But it's impossible that my sample is gonna exactly match the population of interest. It's never gonna be identical, right? If we carry it out and if we have sufficient precision in our measurements, it's always gonna be difficult to different to some degree. It's never gonna be the same, okay? And the difference between what my hypothetical population parameter is and my sample statistic, what is that? It's sampling error. I want everybody to get up out of their chairs right now. Stand up. All right? Put your hands in the air, wave them around, and read this. Sampling error is error or discrepancy between a sample statistic and a population parameter. Okay? Do it again, because I didn't hear you. I heard me, I didn't hear you.
Sampling error or discrepancy between
I need your hands higher. Okay. Because what you're going to say is like sampling statistic is biased in my statistic. It's not. It's very literally the difference between my hypothetical population parameter and my statistic that I get from my sample. I don't know if this is going to work. This is experimental. I've never had people do this before, but people have a hard time remembering this. This is weird, so hopefully remember this enough, right? You can go ahead and sit down, okay? Let's say here, we've got a population of 1,000 college students. And these are all people, so these 1,000 people are my population of interest. There's no other people of interest. This is 1,000 people who are of interest to me, right? And I go through and I measure age, IQ, and gender and sex breakdown for this. Average age, 21.3, average IQ, 112.5, 65, 35, female, male breakdown. These are my population parameters. Now, in general, we can't ever estimate. We don't know what our population parameters are. There's some hypothetical number out there in the universe, but in this case, we do know what they are, okay? But let's say I go through and I take 2 samples. Now, these aren't very good samples because they're 5 people, right? But we got sample 1, sample 2. These are the people in sample 1. These are the people in sample 2 who we've drawn from this population of 1,000 people. In this case, average age, just under 20. Average IQ, 104.6. 60-40 breakdown. Here, average age, 20.4. Average IQ, 114. 40-60 breakdown, okay? This is my sampling error, right? The difference between these statistics and what are these population values and these numbers that I've got from my sample statistics, this is my sampling error, okay? Now these, I'm getting age stayed pretty stable, although both of these are lower than what I've got here. My IQ jumped around quite a bit, right? My population value is somewhere in between. I did a complete reversal in terms of the gender breakdown, 60-40 to 40-60, right? But this is what we're talking about when we're talking about sampling error, right? Now in this case, I've got kind of crappy samples. I don't know how I sampled these, but they're just crappy because they're small, okay? Am I ever going to get rid of sampling error? Never. What if I have the very best methods? Still going to have sampling error, right? Now there are some certain things that we can do to reduce sampling error, right? And these are things we should do. If we think about factors impacting sampling error, sample size. Again, Laura, so why, you had mentioned sort of, in terms of samples, we want bigger is better, right? Why is that true?
I think it gives us more power.
Gives it, well, it certainly gives us more power. Yeah, that's good. Hold on to that. That's several steps above. In general, if we're thinking about sampling error specifically, why are bigger samples better?
Well, it includes more of the population.
Okay.
So you're more likely to see the same distributions that you would see. In
Right.
population.
Right. I'm getting more people. I'm getting a higher percentage of my actual population of interest, even if that's an exceedingly small increase. But I'm getting a more representative example, right? And so as my sample size increases, my measurement error theoretically is going to decrease just because I've got more people, okay? Also sample selection. Who have I not picked on?
Evelina.
Evelina. Why is my sample selection going to make sense or make an impact on my sample sampling error?
Yes, because it would matter like what part of the population you're choosing. So if you're choosing like 2 different groups, then that would differ.
Right, right. So if I'm interested in average income of people in the U.S., right, and I go through and I just get a list of everybody's email, who has an email in the U.S., and I'm like, hey, how much you making? They're like, hey, this is what I make, right? And I randomly select from everybody who I have email addresses for, right? That's random sampling, right? What's the drawback of that? Where is my sampling error going to come in?
You only have people's email addresses.
Right. And in general, people who have email addresses are, what's that relation to income likely?
Higher, probably.
Yeah, we're probably going to miss people who are on the low end of the spectrum who don't have access to email or have accounts or things along those lines. So systematically what I've done with my sampling strategy is excluded people on the low end of the spectrum, and so I'm going to have bias in my sample, right? So how we go through and how we select this sample is going to be important in terms of reducing sampling error. Random sampling is our gold standard. If we could ever achieve that, that would be the best case scenario. But We can't, we don't. Which doesn't mean we shouldn't do research, it just means we need to be aware of the limitations of our sampling procedures. Okay? And finally, a measurement tool. Kate, can you tell me how might a measurement tool impact sampling?
I mean, if it's not like a valid one or it's not reliable or something, it depends. It could just produce like different results that way.
Yeah, yeah. So let's say I'm interested in, I'm running a study, it's in a eating lab, and I might want to see how much people weigh, right? And so feel free to borrow this if you'd like, but students come in, participants come in, and you just grab them, kind of pick them up and be like, I give you $1.20 and just write that down, right? Is that a good measurement tool?
Probably not.
Probably not. I'll probably be able to figure out the difference between someone who weighs 200 and someone who weighs 120, but it's not going to be good, right? My sampling area is going to be all over the place, right? And that's funny because we would just put someone on the scale and record their mass, and then that's probably a better way to do that. But when we start thinking about how we go through and measure some of our psychological constructs, right? We're measuring things that aren't real. They're not physical things, right? But why not just make up my own measure and just give it to somebody? Because this is my measure of social anxiety because I say so, or this is my measure of neuroticism just because these were the 3 items that I felt like I could put on here, right? Functionally, it's the same thing, right? This is why psychometrics and having good measurement tools are so important for research, because if we don't, you just added a whole lot of static into stuff, right? Maybe you're measuring what you think you are, but also maybe not. You might be measuring something very different than what you think you are. So in terms of thinking about reducing sampling error, we want to have good measures, we want to have big samples, and we want to make sure that our sample selection is as good as we can get it, right? Which, oddly enough, this is often the thing that we have the least amount of control over in terms of our methods, but all things to keep in mind, okay? All right, so once more, very literally, sampling error is the difference between your population parameter and your sample statistic. That difference, that's all sampling error is, okay? But these are the things that we can do to try and manage that, bring that down. Questions on this? All right, cool. So again, methodology huge in determining the precision of your data, right? And so particularly if you're working, you don't have a whole lot of people and you don't have resources, you think I'm going to be working with small samples, the best thing you can do is try and make sure that your measurements are as good as they can, that you've got as many people as you can. These are the things that can often mean the difference between having a project that turns results that we can identify as statistically significant versus stuff that we are left saying, well, there might be something there, there might not be, I just can't tell based on these data. All right, constructs, okay. Theoretical constructs, these are attitudes, characteristics. These are things that we can't physically touch, hold on to, but these are things that are useful for describing and explaining behavior, okay? Aggression, right? Aggression is a construct. We can see physical manifestations of aggression, but aggression in and of itself is not a real thing. It's only a thing because we've created it and decided and agreed that this is something that we're going to call aggression, right? Same thing with extroversion, right? If we want to get into sort of deep into the physics of things, even mass and some of these are still constructs, right? But what we want to be very careful of is making sure that we're very clear on what our constructs are, what the definitions, how we're going through and operationalizing those. Our operational definition, this is indicating how we're measuring observable behavior and using these to define this hypothetical construct, right? If I'm an aggression researcher and I'm working out on a playground, maybe I identify physical aggression as the number of times that a child strikes another child, right? And that's my operational definition of aggression, right? Now, am I going to miss some stuff with that? Absolutely, right? There's other stuff, right? Come up and do that, right? Was that aggressive? I would probably say that's aggressive. I didn't actually hit you, but that's still an aggressive act, right? But with my operationalization of aggression, that doesn't count because there wasn't actual physical contact, right? And so we need to start thinking very clearly in terms of our methodology, how we're operationalizing our constructs, okay? This starts to be essential in terms of thinking about our analyses and how we interpret those analyses, right? I might find that on the playground, there's no difference in aggression between boys and girls, right? But that might be because really boys and girls are not different in their population in terms of aggression, or it might be how I've operationalized aggression that's causing the problem. Or maybe it's the sample. Maybe I just would go to like lab school where you just got a bunch of professors' kids where everybody's, no one's hitting anybody or anything like that, right? And maybe you don't find something there, right? So always important is we're thinking about statistics, and our statistical methodology isn't only about just looking at numbers and telling whether or not p-values are greater than or less than 0.05. A lot of it's going to be thinking about how do we operationalize the construct. Is this a good operationalization of the construct? And recognizing that our analyses we're performing these on numbers, right, that are imperfect indicators of our constructs, right? I say, oh, this is a relation between VDI or depression and PTSD. Well, my measure of depression is a back depression inventory, which is something we often use to measure depression, but that's not a literal manifestation of depression, right? There's a lot of other stuff that goes into that, right? Same thing, I can go, and this is one of my peeves as a PTSD researcher. Someone goes through a PTSD checklist, common measure used to assess symptoms of post-traumatic stress disorder. I can give a PCL to everybody in my Gen Psych class, and they're going to fill it out and give me numbers back, right? Can I interpret that as symptoms of PTSD? No, right? Because I didn't administer that to an appropriate population, right? We need to have a criterion event. We need to have some traumatic event that we're having symptoms in response to. Now I can physically go through and I'll get numbers. That doesn't necessarily mean those numbers mean anything from an interpretive standpoint. So these are all things to be thinking about. Our measurements are not our constructs, right? And making sure that we're thinking about that, okay? And so again, we can crank out numbers so we're blue in the face, but our data, our inferences are only as good as our methodology, right? This happens to statistical consultation quite a bit. It's like, well, I did this and that, and everything's all over the place, but how do can I do something to fix this? Like, nope, there's no fix. It's just bad numbers, right? I can't magic up a way to make this not good, right? This was something that needed to be thought about in the design phase, right? Once we've got the numbers, there's no way to control for horrible methodology or the fact that your research assistants were all over the place in terms of how they're executing your experiment and things like that. So always important things to think about. Discrete continuous variables. If we're thinking about discrete variables, these are measurements that have separate indivisible categories, right? These are things like rooms in a house, right? You can't have half a room in a house. Either you have a room or you don't have a room. You can't have a 5.5 on dice, right? So I can roll dice a number of times, and then I can take the average of the number that I rolled, but that's not a real thing, right? That's not an actual representation of something that I could have on that. And so we start to become limited in terms of the analyses that we can run with discrete values versus continuous values. This is some variable that has an infinite number of values that fall between any two observed points, right? I can take a tape measure and measure height, right? But depending on the precision of my instrument, I can get increasingly down to microns of height if I decided to measure it at that level, right? That's a continuous construct, mass, temperature, time. These are things where we can get down theoretically to infinitely small measures versus the number of children you have. Either have 1 or 2 or 3. We can't have an infinitely small number of divisions between children, okay? And so from a theoretical standpoint, this is going to be the difference between what we're talking about, discrete variables and continuous variables. When we're actually working with data, though, this starts to become a little bit mixed. If we're thinking about levels of measurement, right, this is going back to some very basic types of things, but this starts to become important because the level of measurement will almost always determine what types of analyses you would perform. Now, who here the thought of, okay, here's my data set, here's my project, how am I going to analyze these data? Who gets terrified by that? Show of hands. Good, we got some people who are honest, right? What do I do? All right, these are the data. What do I do with these? First thing you should always do is think about what's my level of measurement, because your level of measurement is going to start to shoehorn you into a much more manageable number of options based on the data you have. If we're talking about nominal data, this is categorical data with different names, okay? These are things that we are saying this is different than this, right? But there's no natural order to our nominal scales, okay? We can run analyses that are looking at relations between nominal variables and other things, but no information regarding magnitude, direction of these differences, okay? Can someone give me an example of nominal data? Yeah.
Your rank in the Navy?
What's that?
Your rank in the Navy or?
Not quite, actually, because your rank in the Navy, there's if we were, it depends on what we're trying to use that for, right? If my rank in the Navy is a proxy for experience, then there's some order to that, okay? What would be categorical data with no, there's sort of no meaningful difference between orders?
Race.
Race, ethnicity, yep. That's a category, right? It's not like sort of, hopefully, no one's thinking about ranking these in orders of sort of worth or value or any other such thing, right? So ethnicity, right? Gender, what else? Yeah.
Political party?
Political party, yeah, what else?
Favorite color.
Favorite color, brands of car, right? These are things that just are, right? Type of beer that you like, right? There's no measurable difference or distance between those categories. They just are things, right? This is different than our ordinal scale. Technically, our ordinal scale also categorical data, but here we have categories organized in a meaningful sequence, okay? We rank these in terms of size, magnitude. They have inherent direction, but no standardized difference in magnitude between different steps, okay? The main thing to think about with our ordinal scale, difference between values not necessarily equal, right? And so if you're thinking about our rank in the Navy, I would identify that as an ordinal scale, right? So as we go through, that's a general indicator of power, experience, accomplishment, things along those lines, right? So I can take a meaningful difference between a private and an admiral and say, or seaman and an admiral, whatever they are, right? And I can say, this is a meaningful distinction between, I know, based on this, I know that there are differences in terms of this quality, right? But the actual meaningful difference between, as we start to step up, and I don't know ranks of the Navy, but as we go through and step up, in general, sort of this person's probably been in service longer than this person in general, but it's not like this is the exact same equal thing across, okay? Other examples of ordinal scales.
College football rankings.
College football rankings, right? So we generally say that this person is, this team is better than this and sort of moving up, right? What other types of ordinal scales can we think about? Yeah.
Best cities to live in?
Best cities to live in, okay, based on stuff, right? How about our self-report scales, our Likert scales? I'm gonna rank happiness on 0 to 8, right? That's ordinal, right? I can't 5.5 is not a value on there that I can achieve, right? Laura is a 5, Haley is a 6, right? But I don't know that that 1 point difference is the same as the difference between a 1 and a 3, or a 1 and a 2, or a 7 and an 8, right? We treat our ordinal, our Likert scales as if they were continuous, but they're actually not, right? I can't go through and say, okay, so I can't put whatever value between 0 and 10 I want to on there, and even if I could, there's no way to say that this difference of 1 point on this end of the scale is identical for this scale, and for one person's difference, it's not the same as the other person's difference. Important to recognize that many, if not most of our measurements, we're measuring things on ordered categorical data, even though we treat it as continuous. Okay, so something important to think about. When we jump up to interval scales, these are a set of ordered categorical categories exactly the same size in equal intervals. Okay, so the main thing with our interval scale, distance between all scales or between all units are going to be equal. Okay, so but the thing that makes an interval scale is that the 0 point on our interval scales is arbitrary. Right. The thing to remember is that if I score 0 on an interval scale, it doesn't mean that I have an absence of something. It just means that I happen to have scored 0 on that thing. Okay. Examples of interval scales. Yeah. Temperature, right? I can score 0 on a Fahrenheit scale, right? That doesn't mean the absence of temperature. That's just 1 point that's an arbitrary 0 point, right? But what makes it different is the difference between 5 degrees and 10 degrees is the same amount of difference as the difference between 10 and 15, so on and so forth, right? The scaling is identical throughout the whole level of measurement. It's just that 0 point is arbitrary, okay? So things like IQ, SAT scores, time, right? These are all going to be sort of equal intervals, but that 0 point is arbitrary. Ratio scale, this is just an interval scale with an absolute 0. 0 on an interval scale means that there is actually literally none of this, right? And so if we're thinking about height, mass, speed, income, right? If I'm measuring income in dollars, the difference between 5,000 and 10,000 is the same as 10,000 and 15,000. But if my income is literally 0, that means literally I have no money. It's absolutely gone, right? And so this is the type of thing we'd be thinking about a ratio scale. Okay. And so why this is important outside of just general trivia stuff is starting to think about how we measure things, how we run our statistics, how we're fitting all this stuff together. Very broadly, we can think about variables being discrete versus continuous. But with under this discrete, we can have nominal and ordinal data. Continuous, we typically categorize that as our interval and ratio data, although oftentimes we treat that ordinal data as if it were continuous, right? And you hear rules of thumb, you know, if you've got 5 or more values on your interval scale, on your ordinal Likert scale, then you can use that as continuous data. But as our statistical tools start to get better and better, people are starting to have a harder time with treating those data as continuous. We get into statistical modeling types of stuff. You know, we say, oh, well, I'm going to have ordinal or my Likert scale. I'm going to use this as continuous using a continuous estimator. That's starting to become less and less acceptable as we have other alternatives that are better that account for that ordered categorical nature of some of our Likert scales. Yeah.
What was the number you said that generally the ordinal scales are then continuous?
Ignore that. Okay. So this is the thing. We sometimes will use rules of thumb, but rules of thumb are awful because they provide no context, and people like to hold on to those as if they were dogma, and it's just not. I mean, you could probably, we'll talk about your average C-test, you could probably get away with 5 values, right? But if you were using a different analysis, maybe not, right? And so these are the types of things that we want to be aware of, and this is where oftentimes, you know, our choice in applied statistics is which one of these is my least worst option. Other questions? Okay, so this gets tricky, but sort of wanting to think about, okay, what am I measuring? What's the level of measurement? And 9 times out of 10, that's going to help starting to direct you to what type of analysis I'm going to use in my data. Okay. So again, type level of measurement crucial for selecting your analytic approach. Some mathematical notation. These are variables. It's straightforward stuff. Summation. This just means just add up all the variables after that summation. Sometimes sigma terrifies people. Anybody terrified of sigma? Like get a panic attack if you see sigma? No? Sometimes it happens. It's fine if you admit it. It's cool. Just don't worry. It just means just add up everything after that. So as we go through, we won't use a whole lot of mathematical notation, but it will come up from time to time. So final thoughts on today. Howell has a nice quote, statistics, a subject not merely cut and dried set of facts, but rather a set of facts put together with a variety of interpretations and options, okay? When you get to, you guys are kind of at the highest level of education in a doctoral program. We're no longer just pointing and clicking in SPSS and interpret and sort of calling whatever comes out as significant or not. There's a lot of stuff that goes into selecting appropriate, I like this, you can't fix by analysis what you bungled by design. You'll have a different class on research methods. These two should probably be taught hand in hand because these two things go together. You can't separate the two. Always want to make sure that you're selecting good measures, that you're selecting good designs, that you've got standardization, because that's going to help reduce that error. That's going to help you find the things that you are looking to find. And this is a quote by one of my friends. There are statistics that we're not their people. Right? You're in control of the analyses that you run. Like, you're in charge. You don't just like randomly report whatever SPSS gives you, right? So one, you think, use common sense. Does this stuff make sense? And from a very literal standpoint, if I run these analyses, what does this mean? Like, based on what this analysis does, what does this literally tell me about sort of the relation between these variables? Sometimes interpretations can get overwhelming, and when I get overwhelmed, I say, okay, if I have to put out in words very literally, what does this statistic mean? And if I can write that out, then I can start working on conceptually, how does this all fit together, right? And if you can do that, you're in far better shape than trying to use stock language for, oh, this is what I say when this thing happens, okay? But don't worry, we'll get you there. All right, final thoughts, right? You got 100% from you guys, not 100% and 10%, because that's impossible. If you think you do 110%, you have to apply by the rules of math. So, any questions with stuff? Feeling good about things? Okay, cool. What we're going to do, oh, that's cool.